The dinosaurs did not see it coming, not a single one. No warning, no darkening sky, no ancient instinct that could have prepared any living thing on Earth for what was about to happen. On the morning of what researchers now know was a spring day, the Hell Creek ecosystem was simply living, feeding, hunting, breathing. Then, in the time it takes to blink, the most violent sequence of events in the history of complex animal life began. This is that single day, the last normal morning, the impact, the hours that followed. What came after, the months of darkness and collapse, belongs to another story. This is the day itself. The Hell Creek ecosystem of late Cretaceous North America was not a world in crisis. Geological analysis of the formation shows no significant ecological stress in the period immediately before the impact. It was a warm, humid floodplain. Subtropical, covered in dense forest, broken by rivers and open coastal plain. Richer, warmer, and more biologically dense than almost anything alive in North America today. Herds of Edmontosaurus, duck-billed dinosaurs the size of modern elephants, moved through the lowland forest. Triceratops grazed in open areas. Ankylosaurus, armored from nose to tail, pushed through undergrowth. And somewhere in the tree line, Tyrannosaurus rex, warm-blooded, perpetually hungry, always moving. Pterosaurs rode thermals overhead. Crocodilians patrolled the rivers. Small feathered dinosaurs, the direct ancestors of modern birds, moved through the undergrowth. And in burrows and beneath tree roots, small mammals waited out the daylight, as they had done for millions of years. None of them had any concept of what was coming. We know the approximate time of impact from a remarkable piece of evidence. In 2019, paleontologist Robert De Palma and his team published findings from the Tanis site, a fossil bed in North Dakota that captured the immediate aftermath of the impact in extraordinary detail. Fossilized fish at the site show growth rings consistent with spring. The last day of the dinosaurs was, in all probability, a spring morning. The trees were budding, the rivers were full. Everything was, by every available measure, normal. Then, suddenly on one fine day of spring, the last normal moment ended. The asteroid had been traveling through space for billions of years before it found Earth. It was roughly 10 to 15 kilometers in diameter, about the size of a small city. It entered the atmosphere at approximately 20 kilometers per second. At that speed, the air compressed so violently ahead of it that the sky above the Yucatan Peninsula went from clear to blinding in seconds, not from an explosion, but from the superheated plasma of compressed atmosphere being pushed ahead of the rock. Any creature in the region had, at most, seconds of awareness. The asteroid struck the shallow carbonate shelf of what is now northwest Yucatan, a site called Chicxulub. The location mattered enormously. Research published in the journal Nature Communications found that the shallow carbonate and sulfur-rich rock of the impact site released far more climate-altering gases than a strike on deeper ocean rock would have. The worst possible geology in the worst possible place. The energy released at impact was approximately 100 trillion tons of TNT equivalent, around 1 billion times the largest nuclear weapon ever detonated. The crust at the impact site was vaporized in milliseconds. The resulting crater, about 180 kilometers across and 20 kilometers deep, formed in under 10 minutes. A ring of mountains taller than the modern Himalayas rose from the rebound of the crust and collapsed again before the dust settled. In those 10 minutes, more energy was released than in any event since the formation of the Moon. But the crater was just where it started. The shockwave from the impact reached North America within minutes. The ground in the Hell Creek region shook with an intensity that dwarfs any earthquake in recorded history. Trees fell, riverbanks collapsed, large animals were thrown off their feet. But the shockwave was not the main event. The main event was what went up. The impact launched billions of tons of vaporized rock and molten debris upward through the atmosphere and into space. That material then re-entered the atmosphere on ballistic trajectories, not just over the impact site, but globally, across every continent, within roughly 60 to 90 minutes. As it re-entered, it heated the air through friction, everywhere, simultaneously. A 2017 study by researchers at the Lunar and Planetary Institute modeled this re-entry heating in detail. Their findings were stark. The radiant heat pulse at ground level across large areas of North America would have been sufficient to ignite dry vegetation and kill unprotected animals within minutes, not from fire falling from the sky, but from intense infrared radiation, like being placed inside a broiler. The Hell Creek ecosystem, which had been alive an hour earlier, was burning. A T-Rex in the open during that heat pulse had no survival pathway. No speed, no size, no physical adaptation could protect a large animal from radiant heat intense enough to ignite wood. The giants of the Cretaceous were, in the most literal sense, cooked where they stood. Animals underground fared better. Research into which lineages survived the extinction has consistently found that burrowing ability was one of the strongest predictors of survival across species. The small mammals that would eventually inherit the Earth were, in this moment, saved not by their intelligence or adaptability, but simply by the habit of hiding underground. Accident, not fitness, determined the first survivors. While the heat pulse swept continents, something else was unfolding at the impact site. The asteroid struck shallow water. The displacement generated a tsunami unlike anything in recorded geological history. Modeling published in AGU Advances estimated initial wave heights near the impact site at over 1 kilometer. As it spread outward across the Gulf of Mexico, it lost height but gained reach, penetrating hundreds of kilometers inland across the low-lying coastal regions of what is now the southern United States. Geological evidence of this wave has been confirmed at sites across Texas, Alabama, and the Caribbean. Layers of violently disturbed sediment, out-of-place marine fossils, and massive sand deposits that carry the unmistakable signature of catastrophic inundation. The Edmontosaurus herds of the coastal lowlands, which had been grazing hours earlier, were swept away in water carrying debris, sediment, and the wreckage of a world. Within 2 hours of impact, the most powerful shockwave in the history of complex life. A global heat pulse igniting forests across multiple continents. A tsunami reshaping the coastlines of the Americas. And the day was not yet half over. Hours after impact, the ejector, still coming back down from space, was seeding the upper atmosphere with fine particles. Dust, soot, and sulfur compounds from the vaporized Yucatan rock. The sky was not yet dark. That would come over days and weeks. But the light was wrong, filtered and reddened through thickening layers of debris. A 2020 study in the Proceedings of the National Academy of Sciences found that the sulfur released from the Chicxulub carbonate rock alone was sufficient to trigger a decade of global cooling, the mechanism that would, in the coming months, collapse photosynthesis worldwide. But on this day, for the animals still alive, the sky simply looked wrong. The air smelled of smoke and sulfur. The temperature, which had spiked violently during the heat pulse, was beginning to drop, the first faint signal of the winter that would follow. By the time ordinary darkness fell that evening, The world was unrecognizable. Fires burned across vast areas of forest and open plain. Rivers ran dark with ash and debris. The air carried sulfur, and in the landscape that remained, the animals that had survived the day were alive. But the world that could sustain them was already gone. A T-Rex that had survived, sheltered in dense forest, positioned far enough from ground zero that the heat pulse was survivable, was still breathing as night fell. Still hungry. Still, in every biological sense, functioning. But the Edmontosaurus herds that fed it were dead or scattered. The vegetation that would regenerate those herds was buried in ash or burning. The food web that had supported the apex predator of the Cretaceous for millions of years had been severed at multiple points, simultaneously, in a single afternoon. We can read all of this in rock. The Cretaceous-Paleogene boundary, the geological layer that marks this day, is visible in outcrops on every continent. It is a thin band, often just centimeters thick, enriched with iridium, an element rare on Earth's surface, but abundant in asteroids. The identification of this iridium layer globally, first published by Luis and Walter Alvarez in 1980 in the journal Science, was the evidence that finally confirmed an extraterrestrial impact as the cause of the extinction. Below the boundary, Cretaceous fossils, rich and diverse. Above it, almost nothing. 66 million years of biology compressed into a layer you can cover with your thumb. The dinosaurs did not decline. They did not sense it coming. They were removed with geological suddenness on a single catastrophic day, by an event so far outside the parameters of normal existence that no evolutionary preparation could have helped. The last T-Rex didn't die on impact day. It died days or weeks later, in a landscape it could no longer feed from, under a sky it had never seen before. But the last normal morning, the last moment when the Hell Creek ecosystem was simply itself, ended with a light in the sky that no living thing had ever seen, and none of the giants would ever see anything again. What happened next? The months of darkness, the collapse of food webs, the slow end of everything that remained is covered in our previous video. The day was one thing, what followed was another.